In this video, we're going to try and understand why it is that when you differentiate the unit tangent with respect to time, and when you differentiate the unit tangent with respect to arc length, they will both be orthogonal to the original unit tangent. So when you differentiate the unit tangent, so this is your unit tangent, with respect to time, it will give you a new vector. This new vector will be orthogonal to the original tangent. But the thing is, when you differentiate it with respect to arc length, it will also, so when you differentiate it with respect to arc length, it will give you a different vector. And this vector, this different vector, will also be orthogonal to the original tangent. So when you differentiate the original tangent with respect to time, it will be orthogonal to the original. When you differentiate it with respect to arc length, it will also be orthogonal to the original tangent. So we're going to try and understand why that is. Okay, so to compute the unit normal, we would normally do this. We would differentiate the unit tangent with respect to time. So that would then, so when you differentiate the unit tangent with respect to time, that would then give you a new vector. So you get this new vector, and then you divide it by its magnitude. So let's imagine the magnitude is 3. So you divide it by 3, and then that will give you a unit normal. So that has always been our routine. So we're going to try and understand why it is that when you differentiate this with respect to arc length, it will also be orthogonal to the unit tangent. So let's try and understand why. So going back a while now, the curvature is defined by this. Well, we don't really know what this means. Differentiated with respect to arc length. You see, we can easily differentiate it with respect to time because we've done it many times. You would just shut off your brain and just differentiate it with respect to time. It's quite easy. But with respect to arc length, it's a lot harder. You have to think of the particle moving along the actual path or the actual curve, and then see how the unit tangent changes with respect to the arc length. It's a lot more complicated. But when it's with respect to time, it's nice and easy. You can just shut off your brain and do it. So the curvature is given by this. The normal, and then remember this is a definition. The normal is saying differentiate the unit tangent with respect to arc length, whatever that may mean, and then divide it by its magnitude. Don't forget, notice that this thing here is exactly the same as this. So what it's saying is differentiate it with respect to arc length, whatever that means. So let's just imagine it to be this new vector here. And then because this is the same as this, it's just saying divided by its magnitude. So the normal is easier just to visualize it like this. Differentiate the unit tangent with respect to arc length. Let's just imagine it gives you this thing here, and then divide it by its magnitude. Let's just imagine the magnitude is 3, so you divide it by 3, that will then give you your normal of length 1. So that's what it's saying. But the thing is, we don't fully understand what it means to differentiate it with respect to arc length. So let's use a chain rule here. We've done this technique before. Imagine it with respect to time, and then dt over ds, and then in a way these two cancel each other out. So that's us applying the chain rule, and I've already done an explanation as to why you're able to do this. I've already done a video on this, and then so rewrite this as this dt over ds. So in a way they cancel each other out, and then imagine this as this thing here, one thing times another thing, and then when you look at this quantity here. This block will always be positive. It will never be negative, because as the particle moves along here, dt, the change in time, is always going to be positive. We're not going to go back in time. And then this ds here, as the particle is moving along, ds will always register a positive distance along the path. It will always, so this quantity here will always be it will never be negative, because dt, as the particle is moving along, time moves along, and the time will be positive as the particle is moving along. And then this distance here, as the particle is moving along the path, the ds will also be positive. So this thing here will never be negative. Well, if it's never negative, then that's the same as this thing here, because here it's saying ignore the negative version, even if it's negative. So in a way, these two cancel each other out, giving you this. So we started out with the definition of normal being this thing here with respect to ds. We don't really understand what it means. So we started out with this, with the normal being defined as this with respect to ds, even though we don't really understand what it means with respect to ds. But then we manipulated it, and then it took us to here. So the unit normal is really us differentiating the unit tangent with respect to t. Now it's with respect to t. So and then you divide it by its magnitude. But the point is that we started out with ds, but then a bit of manipulation, it boils down to us differentiating it with respect to dt with respect to time. So going back to the start of the video, why is it that when you differentiate, well, in a way, when you differentiate this, a bit of manipulation, and it really boils down to us differentiating this with respect to t. That's why it's the same as this. I hope you can follow that. Yeah, I hope you can follow that. Okay.